So good evening to everybody, and welcome back to this thematic session on the quantum mechanics and spectral theory. As you see in the program, we have this evening a long session with 10 contributed talks, which are scheduled in 2 hours and a half. So I recommend all the speakers to respect sharply the schedule. And as already announced, the talk consists of 15 minutes, including questions. So if you like to have questions, conclude a couple of minutes before what is written in the schedule. So our first speaker is David Gontier. Okay, switch to the slide.
Okay.
And he's going to talk about crystallization in Lieb-Thirring inequalities.
Thank you, Gianluca. So I will present some recent work we did on the Lieb-Thirring inequalities together with Rupert Frank and Matthew Levin today. So let me first recall what is the Lieb-Thirring inequality. I choose D a dimension and gamma some power. And there is some small restriction on gamma. It must be bigger than 1 minus D over 2. Then for all potential V, like this, you want to count the number of eigenvalues of the Schrödinger operator minus Laplacian plus V. And the Lieb-Thirring inequalities tells that the sum of these eigenvalues to the power gamma, so you only have to take the negative eigenvalues here, is less equal than a universal constant independent of V times this norm of V, the LP norm of V. So it was derived in 1975 by Lieb and Thirring. They also have some version for the critical case, where here you have equality in dimension 1. So it holds also for gamma equals 0 in dimension, gamma equals 0 in dimension D greater than 3. This is called the Zwickel-Lieb-Rosenblum inequality. And for gamma equal 1/2 in dimension D equal 1. So there are 2 key remarks I want to make here. In the case gamma equals 0, the eigenvalues to power gamma is just 0 or 1. So the left-hand side just counts the number of eigenvalues. It tells you that for V in L D over 2, then the number of eigenvalues is finite. The second key remark that I will use today is that on the right side, you have an extensive quantity. So the potential V, if it is a contribution of 2 potentials, say, one on the far left and the other one on the far right, then the right-hand side splits. So you expect the eigenvalues of the system to be somehow the eigenvalues on the left side plus the eigenvalues on the right side. It's not exactly exact, because you have some tunneling effect between the eigenvectors, but this is what is expected. This inequality plays a major role in the study of large fermionic systems, and it was used, for example, by Lieb and Thirring for the proof of stability of matter. I will, in this talk, focus on a finite rank version of the Lieb-Thirring inequality. So here the main difference, the only difference with the previous slide is the disappearance of n. So I'm considering only the sum of the n first eigenvalues of this Schrödinger operator, and I call Ln the optimal potential for this inequality. If I take n equal 1, it's a small exercise to prove that this inequality is equivalent to Galviardo-Nirenberg. There is another constant which plays a major role in the study of this inequality. It is called the semi-classical constant. If you take any V, then in the limit h bar goes to 0, this is correct. This quantity converges to leading order to this quantity. So in view of these 2 inequalities, the finite rank and semi-classical, you can directly see that the best quantity for the Lieb-Thirring is greater than Ln for all n, and also greater than the semi-classical limit. And so there was a famous conjecture by Lieb-Thirring down here that L is actually equal to this maximum of L1 and L semi-classical. And I want to talk today that I want to say that this is more complicated than that. So the key questions in the topic is, what is the best value L? And can you find an optimal potential for L or for this version, the finite rank version of L? So let me recall what is known on the Lieb-Thirring inequality, and including our last result. So first, the ratio L of L semi-classical is decreasing. I recall that L is always bigger than L semi-classical. So once it touches 1, this quantity is always bigger than 1, and when it touches 1, it stays at 1, because L can be only bigger. I will call this the first point where you have this ratio equal to 1, gamma c of the dimension. In dimension 1, it is proved that gamma c is equal to 3/2. So actually in 3/2, L is equal to Ln for all n, and is equal to the semi-classical limit. So here we also, this was known since the paper by Lieb-Thirring, that the only optimizer here are what is called solitons. N solitons will give you Ln. If you take the power bigger than 3/2, so 3/2 is somehow the critical, one of the critical exponents here. L is equal to L semi-classical in all dimensions. In dimension 1, for gamma equal 1/2, which is a critical case, L is equal to L1, so here we have the Gagliardo-Nuremberg constant. And finally, if gamma is strictly less than 1, we know that L is strictly bigger than L semi-classical. I will recap everything with this figure. So the new result we have with Rupert and Mathieu is the following. Assume gamma is bigger than 2 minus d/2, then L2n is strictly bigger than Ln. In particular, the best constant in Lieb-Thirring cannot be given by an n-bound state potential. So this is what is known. In dimension 1, for example, we know that there is a semi-classical regime after 3/2. Here it's not defined. At 1/2 we have the one-bound state, and here we cannot say anything. For dimension 2, we know there is some point, crossing point. We also know that this crossing point is after this value, 1.165 and so on. Below, it cannot be semi-classical, and cannot be an n-bound state because of our theorem. So the optimal potential must have an infinite number of bound states, and this is what we call crystallization. Some big cluster is forming and cannot be a flat cluster because the flat cluster corresponds to semi-classics. Finally, in dimension 3, we also have the same phenomenon, not semi-classical, then we know that crystallize, and then it is semi-classical, so that you recover some flat constant, like you have to think of it as a liquid phase, and the blue part would be a crystalline phase. And I will show some picture afterwards. So how do you prove L2n bigger than Ln? The new result, I will do it in a simple case, L2 bigger than L1. For L1, because it's Gagliardo-Nuremberg, we know everything about this inequality. In particular, we know that the optimizer is given by this function Q, which is the optimizer in Gagliardo-Nuremberg inequality and solution to this equation. And once you know what is Q, then the best potential is this V, which is Q to the 2 p minus 1, where p is a dual exponent of gamma plus d/2. So what we did is to consider, to split this potential, to duplicate this potential on the left and on the right, but we do not take the sum of the potentials directly. This will fail. We take a combination of the density. So we take Q square, which corresponds to some density. We translate it to the right. We add the same contribution to the left, and we take the p minus 1 version of this. So that is the main trick we use, and we noticed that we had to add the densities and not the potentials. If you do that, you do some computation, and you have this line. You can take this as a test function for L2, and you have this. That L2 must be bigger than L1, 1 plus this factor, this exponential plus this exponential. So here you don't know yet that this is not this is a leading order to compare to this correction, but it is the case when p is smaller than 2. And to say that p is smaller than 2 is exactly our condition gamma, which is a dual exponent here, bigger than 2 minus d/2, and this is how we get our condition. This condition is optimal in dimension 1 and after 3. In dimension 1, we know that L2 must be equal to L1 at the point 3/2, the critical point 3/2. And in dimension d greater than 3, for the critical case, the CLR case, we know also we have equality. So this is somehow optimal. OK, so let's talk about crystallization. I just want to show one beautiful picture afterwards. So we know that the best potential somehow have an infinite number of bound states. And the semi-classical version, you have to think of it as a flat V. So this leads to us to study the periodic version of Lieb-Thirring inequality, which takes the following form. You take the same as a Lieb-Thirring gamma greater than 1, maximum 1 minus d/2. Then for all periodic V, this trace, so this is some kind of trace per unit volume now. So this is the sum of eigenvalues per unit volume, is less than this same constant L times the integral per unit volume of V. But now, we can talk about optimizers for the semi-classical case, because now V equal constant is in this space, is a periodic function. It is not an LP space, so semi-classical is never attained usually, but once you periodize everything, V equal constant is an optimizer in the semi-classical case. Otherwise, you can find crystallized case, and this is what we found numerically. So for example, in dimension 2, we found this configuration of electrons in the triangular lattice. So in this picture, so I have some parameter which I vary. You have to think of the parameter as the size of the lattice. The black line represents L1. The dotted line represents L semi-classical. And when I vary the parameters, this is for the triangular shape, there is a regime where the constant I have is bigger than L semi-classical and L1. What is also interesting in this picture is that you see that we assumed that the potential will split, and actually the best potential we have now is somehow a combination of one particle far away from each other. And the gain of energy, I said in the previous slide, we expect it to be exponentially small, and numerically it is. So if I compute the gamma C, the critical point where L becomes L semi-classical, the conjecture of Lieb was this value, 165378, and now our new conjecture is this value, so you see it's not a big improvement of the constant. Let me conclude. So I recall Lieb-Thirring is valid for all gamma greater than 1 minus d over 2, but if gamma is greater than 2 minus d over 2, then we proved that the n-bound state is never optimal. There are still two conjectures which are open. The first one is in dimension 1. Our theorem doesn't say anything in dimension 1, and actually numerics confirm that this conjecture might be true. And the true Lieb-Thirring conjecture, it concerns the case D equals 3, which it is conjecture that the critical point, gamma C of 3 is 1. So we have this inequality, and this is what we need for the study of large fermionic system. OK, thank you very much.
Thank you for this nice talk. Are there questions in the lecture room? No? Then I would like to ask, about the shape of, you say the crystallization is around the triangular lattice in numerical simulations. How far you are from having a rigorous proof of that?
No, we think it's extremely difficult. Actually, we are not, we don't know, there might be also a bounded potential in LP space, which has an infinite number of bound states. This we cannot rule out. So we think also a possible scenario would be a potential LP, but which decays very slowly to infinity and which form like a large cluster of atoms, but which is also integrable.
Okay, thank you. Other question, please?
Sorry, can you do also something for complex valued potential, or in the spirit of the works by Frank and Simon of the last decade?
I'm not sure about that. This is a computation, so where is it? Sorry. You have to compute this leading order. I think it should work for complex potential. The trick is, I think we don't know much about like general Lieb-Thirring for complex potential or with magnetic fields, then it becomes much more difficult to study, also numerically.
Okay, thanks.
Can I ask really quickly, was the plot that you showed a plot of V? Is that, did I understand that right?
That's the density.
It's a plot of the density, okay.
I put some scale. You see the black line is around 100 and the white region is around 0. So there is really a very small interaction between the bubbles here.
David again.
Thank you.
So the next speaker is Alessandro Olgiati, who moved recently to Zurich, and he will talk about bosons in a double well, two-mode approximation, and fluctuations.
Do you hear me? Yes. Does this work? Yeah, it does. OK, thanks a lot for the introduction and, of course, for allowing me to present my work today. Yeah, I will discuss a result about bosons in a double well, which I obtained in collaboration with Nicolas Rougerie from Lyon and Dominique Spener from Concepción in Chile. Right, so in this slide, you should see the model, the full model we studied. You should read the M-body, let me try to, yeah. M-body Hamiltonian for M bosons. This is a Hilbert space for M bosons. And they interact with their interaction in the midfield regime, right? You see a coupling constant 1 divided by n minus 1, and an extra coupling constant here. I'm writing here below the assumptions on V on W. I don't want to discuss them. They're certainly not optimal. But yeah, and for this Hamiltonian, we studied the ground state energy and the associated ground state vector. What is important here, since I want to study a double well potential, is indeed this external potential. And we make the particular choice of the curve that you see here in red, right? So what's going on in this function? Well, we're taking two centers, XL and minus XL, for example, along an axis, let's say, and they have at a distance L, as you should see in the picture. And around those two centers, we take a homogeneous potential, x to the s, okay? And we cut it when the two curves meet over here. We want to study this system in the limit n to infinity, which is typical for large bosonic systems, and in the limit L to infinity, right? And if you look at our picture, it means distant wells, for sure, and also high potential barrier between the two wells. All right. Yeah, in this slide, I'm trying to recap the motivation or like the moral ideas behind our investigation. If we were to keep L fixed, right? So what I'm writing here what's going on here on the left, we would be in a fixed well setting, so the standard mean field regime for bosons, for trapped bosons. And I would say that this problem is by now very well understood. Particles will turn out to be uncorrelated, and there is one occupied mode to the leading order, and this coincides with the Hartree minimizer. And all the other modes in the Hilbert space are occupied only to the next to leading order. They're true excitations. And yeah, this problem has been studied a lot, and here I'm citing 3 papers from which we took a lot of inspiration, even on the technical level. Our situation is different because we study the case in which L goes to infinity. So this is a genuine double well. And it turns out that 2 modes will matter for us to the leading order. And already this, which is already still a simple case, let's say, it's 2 instead of 1, it already gives rise to a rich fauna of possibilities, for example, for the ground state. And one can investigate the following dichotomy, let's say. Is it favorable for particles in the ground state to be uncorrelated and maybe distributed each one of them on a superposition of a left mode and a left well mode and right well mode? Or is it maybe favorable for each particle to choose whether it wants to stay in the left or in the right mode, as here in the right? Yes, these are some ideas to keep in mind. Here I'm resuming what our main results will be for the M-body problem. First of all, we proved that indeed the 2-mode occupation picture is correct. 2 modes are occupied to the leading order. And indeed, we proved that the uncorrelated picture that would hold for a fixed well breaks down for us, right? And we also proved that we also prove an energy expansion in terms of energy of the 2 leading modes and of excitations. These are, maybe I will not have time to go through, but anyway. Right, so the ones I discussed in the slide before are n-body results. But so these are based on an analysis of the one-body model. So let me write here the main players of the one-body model. Of course, standard object is the Hartree functional, which is defined like this and reads as this integral. This is very standard. The Hartree functional has a minimum, E mean field, we call it, and it is attained in our assumptions by a unique minimizer up to a phase, which we call U+. Actually, once you take this Hartree minimizer, U+, you can form, by definition, the linear operator that you read here in the bracket. This we call mean field Hamiltonian, or maybe Hartree Hamiltonian also. You put U+ in this convolution. Now, this is a linear operator, and it turns out that U+ is also the ground state of this linear operator. And we call it's the corresponding eigenvalue mu+, again, by definition. Right? Not only that, but since H mean field, since the external potential here grows at infinity, right, by how we chose it, H mean field has compact resolvent, and it means that we can diagonalize it in terms of pure point spectrum only, well, eigenvalues. And I'm writing here its spectral composition. So I already discussed about this. And we call the first excited mode U-. And mu- is the associated energy, or eigenvalue. And then there is all the rest of the spectrum, which is over here. These are excited mode. The idea you have to keep in mind is we want to show that in the n-body ground state, particles will want to live in the span of U+ and U- to the leading order, and then occupy all the rest as a subleading, in a subleading way. Okay, so if this peak plan has any chance to be shown in the n-body setting, then it's crucial to understand the spectral properties of this Hamiltonian, in particular, the gaps and actually the properties of all the objects that you see in this slide. And these spectral properties are indeed the content of a parallel paper that I wrote in collaboration with Nicolas, really on the spectral properties of this one-body problem. Right, here the crucial parameter is this T. T governs a lot of relevant quantities, and it is defined as this e to the -2 of that weird expression depending on L. L is the distance between the two centers. And for those who know it, this coincides with e to the -2 Agmon distance within the landscape x to the s at the point L divided by 2. Okay. Right, since L for us is going to infinity, I told you in the n-body model, which means that T has to be small, right? Because it's a e to the minus something that grows in L. It turns out that this T captures the first gap of the mean field Hamiltonian that was in the slide before. So this is the first gap, this difference, and it is of order T up to corrections that can also maybe be eliminated. I'm not sure, maybe. Right, so the first gap is small, right? So if a particle occupies the first mode, then it does not pay a huge price to go to the mode U-, to the other one. On the other hand, the second gap, so the gap between mu- and all the rest of the spectrum, is finite. It's bounded from below by a uniform positive constant. So you have to pay a way higher price if a particle wants to jump to an excited mode. Okay, so these are crucial properties. We actually are able to prove more, in particular, some refined properties on the eigenvectors. So we prove, for example, that the absolute values of U+ and U- are closed. And we prove more. We can say that U+, looks like the red curve that is here, and then it's hidden below the blue curve here on the left. So hence the name U+, right, because it's symmetric. And U- looks like the blue curve, hence the name U-. So you should not be too surprised if I tell you that linear combinations of them are localized in the right and in the left. Well, so U right and U left are the modes that we want to focus on to transition to the n-body setting. Okay. Right, so this is our first main result. How do you go back? Yes. So I maybe should say that these results were not present as they are in the literature, but we definitely took a lot of inspiration from results that were present in a slightly different setting, namely in a semi-classical regime within multiple wells, right? And this has been done, studied a lot by Barry Simon and collaborators, and Helfer and Jostron. And yes. But yeah, we definitely have had to work a little bit more, in particular to prove this lower bound on the first gap, which for us is really crucial. Okay, I'm ready to present you our n-body result. I will use the following notation for number operator. This is standard for the left mode and for the right mode. So this is a dagger of u left or u right, and then a of u left and u right. And the main theorem reads as follows. We have to make the important assumption that, so I told you that t has to be small, because L is going to infinity, but we want to take t small as some negative power of n, no matter how small the power. So there exists some delta, maybe very small, it's fine, for which t goes like n to the minus delta. And we also assume that lambda, the coupling constant, is small enough, but of order 1. And then, as n goes to infinity, we prove the two bounds that you see here. Let's look at the first one. Well, the first one says that our two-mode interpretation or approximation is correct to the leading order. 100% of the particles, so n particles, are either in n left plus n right in expectation on the ground state. And then there is an order 1 fraction, which is this c, which is not in those modes. So this is great. It's already something, and it's more or less Bose-Einstein condensation. Okay. And then we prove this mysterious bound that you read here that I would like to try to explain you. So we have n left. Let's see here. Minus, this is expectation, right? It should not be too hard to see from the line above that the expectation of n left on the ground state must be n divided by 2 by symmetry. So we are taking an operator and subtracting its expectation and taking the square and then the expectation. So this is the variance of n left, okay? And then the same we are doing for n right. And we prove that this is much smaller than n. What does it mean? Okay, so it is known that for a single well setting, so if L were to be kept fixed, or in our rephrased, if T was fixed, then I told you already that the uncorrelated particle pictures is a very good approximation, and this means that a central limit theorem must hold for quantum observables. Here I'm writing two papers, in which a central limit theorem has been proven. These are just two I know, and I'm sure there's definitely sure that there are many others. But anyway, the idea of this central limit theorem is that now this operator n left we are in a fixed well setting. It's a collection of n independent, identically distributed one-body observables. You see it here in the first line, and the central limit theorem tells you that the variance of such a random variable, if you want, must be of order n, or if you want that fluctuations must be at a scale square root of n, and then you take the square. And we prove that this is not the case as soon as t goes to as some negative power of n, because that expectation is much smaller than n. So this means that the central limit theorem is violated, and hence it means that particles do not want to really be completely uncorrelated. They want to choose whether they want to go in the in the left well mode or in the right well mode. Now here I have another slide which I will spare you about the energy, the other part of the result, which is the energy expansion, and I think this concludes what I wanted to tell you. Thank you for your attention.
Thank you for the nice talk. Other questions? Please.
Thank you for your talk. I just didn't get really in which order you take the limits L goes to infinity, N goes to infinity.
Right, so I send N to infinity with L going to infinity as a function of N. And in particular, so this T here must be of order N to the minus delta. And T was defined in the previous slide as a function of L. So L has to be some logarithm with some power correction, some logarithm of N. So they are not independent limit at all.
And I guess it's critical. I mean, if you go a little bit faster or a little bit slower, you get different results.
Yeah, so I expect that there should be a, so we can go T can go as fast as it wants to 0, but it cannot be as low as it wants, at least as some power. Probably there is, yeah, if it's lower than some power, than any power, then maybe at some point the result will stop to hold, I guess.
Other questions? Okay, then we thank Alessandro again.
Thank you.
So now we switch to an online speaker. I hope it's connected, Tristan Benoit. Okay, hello, Tristan.
Hello. I hope you hear me.
Yeah.
Okay.
Everything okay? So our next speaker is Tristan Benoit from CNRS in Toulouse, and he will talk about the appearance of particle tracks in detectors. Please.
So thank you for giving me the opportunity to talk about this work today. So it's a joint work with Miguel Ballesteros, Martin Frass, and Jörg Fröhlich. So Miguel and Jörg are at the conference right now. So if you have questions, you can also ask them. So the question, the work I will talk about is about this kind of experiments. So I guess most of you already seen such a video. It's just a cloud chamber with particle tracks appearing in it. And it's actually an experiment that is, when you think about it, a bit more confusing than what you expect, because you see definite tracks with precise velocity and position of particles, while this is not possible a priori in quantum mechanics due to position velocity Heisenberg's indeterminacy principle. So think of, for example, alpha particles that start in the S wave. You don't expect it to have like a precise velocity and location. It's not physical for a quantum particle, at least for a massive one. It's also true that it's true for the state, but also for an instrument. Like an instrument, physical instrument, could not result in a definite position and velocity of a quantum particle. So the question that raises is how do particle tracks appear in these detectors? The question is actually quite old, like at least date back to the beginning of the 20th century with a paper by Mott on alpha particles, particularly. And we tried to answer, at least to give some insight into this problem using approximate measurement, position measurement of particle. So what do I mean by approximate measurement, position measurement? Is just that we have an instrument that doesn't give us exactly the position of the particle, but given the exact position of a particle, we give an approximation. And this is encoded in this distribution here, f, x, q. So q is the approximate position of the particle, and x is the conditioned exact position. So if I start with, think of it as, is this an S wave, so a particle state in L2 of R3, then I obtain a random result to my measurements, which is given by applying the usual Born rule by this distribution of Q0. And then updating, knowing this measurement results my state, either applying Bayes rule or projection postulate, I get a new state and a posteriori state of the particle. What we'll do now is actually not do a one-shot measurement and say, okay, afterwards the particle evolves classically because it has some position, because we don't know velocity. So we cannot say that it has a definite track afterwards. So we'll do an infinite sequence of repeated and fast dominating measurements. What does it mean? That we first, like if we start with the state of the particle psi n at time n, we measure it with this approximate position measurement instrument, and we obtain a measurement result Qn, and an a posteriori, so random one, and an a posteriori state that depend on this result, that is psi n Qn. Then we let the particle, we assume that the measurement is so fast that we can distinguish between the unitary evolution of the isolated particle and the measurement. And so we let it evolve, we let the particle evolve according to the unitary. And then we repeat. And we have, this is our model of particle detector here. So what we get at the end, it's a random sequence of approximate positions, and its law, it's just given by the repeated application of our instruments, the unitary evolution, and it depends, of course, on the initial state of the particle. So this is only like standard quantum mechanics from now. So the first model and simple model we will apply it to is linear dynamics and Gaussian approximate measurements. So first we assume that the dynamics is linear, meaning that when I apply my unitary to my position and velocity operators, it's just transforming them linearly using a symplectic matrix. So this is the case, for example, for a free particle or an harmonic oscillator, or more importantly for particle detectors, a charged particle in a constant magnetic field. So here you see that I highlighted like the different blocks, because these blocks that gives the position of the particle that depends on the part of the position of particles that depends on the velocity will play an important role afterwards. And the most important assumption here is that we assume that the measurement, the approximate measurement is Gaussian. So this is a standard assumption when you try to have approximate measurements. And so we have that the law of the approximate position given a fixed position is given by this Gaussian centered in the true position and with a given covariance. And so F we can typically take F as being this form here. With only these assumptions and just assuming that the position of the particle depends on its initial velocity, then we can construct actually autoregressive Gaussian process here. So this is just the definition up to here of this autoregressive Gaussian process, such that taking a random, like the random starting point for this process that depends on the state and some family of coherent states localized in X and V, then actually we can write explicitly the law of our approximate position measurements, depending on the position of this autoregressive process plus a perturbation. And you see that this autoregressive process is the classical path perturbed by some noise, and that the next step, of course, depends on the previous particle data and also the noise. One of the first corollaries that you can see this as a perturbation of a classical track is just that under the same assumptions as the theorem, if you assume that the moment exists for a position velocity initially, then actually the expectation of the approximate position you are measuring is just the expectation of the position of the classical track. So two remarks here, that we have no restriction on the initial particle state and no extra approximation. We make no approximation here. And we do not assume, compared to other results, that psi0 is a coherent state. And as I already said, the particle position at time n depends on all the previous measurement results. But we want to go a bit further than this model, and particularly we want to generalize what kind of approximate measurement we can do. And that would be the purpose of the last part of my presentation, that now we will consider that the particle in its initial states localizes in phase space into a volume of size epsilon with epsilon very small. So you can typically think of epsilon as 1 over m, and m being the mass of the particle and a very massive particle. So typical scaling of the initial state is this one. And we want to take the observables that you will, so what we look at in the particle as not being like, being stable with respect to the scaling of the precision and the localization in phase space of our particle. So this is this condition, and this is the usual set of symbols in the semi-classical analysis. So these two constructions are summarized here, that we have like our state is localized in a region epsilon in the phase space, while our observable will stay in this region, in this blue region, but we vary along like distance of order 1 while the particle localizes. So we do a usual assumption of localization, and here, which is hidden, is just we quantize our observables, and we just assume that when we take the limit of localization of our particle, our observables will commute. So now with these assumptions, we precise our model. So we first assume that our instrument is adapted to this scale, so that first the instrument stays in this set of symbols. So it means that it won't get more and more precise as the particle becomes localized. It stays macroscopic. And this is just a technical assumption that the function f has to define a good instrument, that it's a stochasticity, and we have some technical assumption. On the dynamics, we assume also that, okay, at the scale we are looking at, so for our instruments or for our observables, what we have that the quantum dynamics can be well approximated by a classical dynamic. So this is typically obtained through Egorov theorem, but also without limits. This is actually verified for a massive free particle, for massive harmonic oscillators, and massive charged particle in a strong magnetic field. Basically, you fix B here, and you take M and B to infinity. So under these assumptions, what do you have as a result? We first, assuming that the initial state of the particle behaves well in this limit of localization, which is summarized here, that it converges towards probability distribution, then actually the approximate measurement process converges in law towards an approximate positions, like independent approximate position of the particle that depends on the classical deterministic underlying path of the particle. That each Q here, that depends on the position of the particle along the classical path at time n, are all independent and are distributed according to our instruments, the functions that define our instruments. To be clear, that if I take a translation invariant instrument under the same assumption, so translation invariant means that I have that actually f can be written as a function of the difference between the position of the approximate position and the true position. Then what I obtain in the limit epsilon goes to 0, so localization of the particle, or high energy, or infinite mass, is simply the perturbation, like the deterministic position of the particle here, xn, plus some random noise and IAD sequence of random variable. So this is like in high energy, because I didn't say it, I just have time for this. This, of course, is also like when you look at here, you see that this is a scaling of the mean velocity of the particle, and this is the mean position, and you see that they scale like 1 over square root of epsilon. So that means that we are in a high energy limit. So from these results, so this is the beginning of our work, and so from this we want to try to find how we can from this data, from the data of the approximate position measurement, estimate the initial data, so the initial, to see that indeed what you obtain from the data is a fixed initial position and velocity, to extend it to open systems to see particularly why you have this modification of direction, for example, in the tracks sometimes. and also to have a limit of precise measurement with also a localization of the particle. And finally, like do the continuous time approximate measurements setup. And that's all I wanted to talk to you, and thank you again.
Are there questions? I have a comment myself. So there is an alternative approach to the Mott problem, namely to consider an array of harmonic oscillators, for example, on a two-dimensional lattice, and to prove that whenever this array of harmonic oscillators is coupled to a tracker particle. And one possible approach is to prove that whenever one of the oscillators initially prepared on the ground state is excited, conditionally on this event, the probability that a second one is excited is maximal along the straight line which connects the two oscillators. And this approach has been put on a solid mathematical ground by Rodolfo Figari and Alessandro Teta. And I would like to ask you to comment on the relation between the two approaches.
So we learned a bit about this. I must say that we didn't have time to really compare our results with theirs. But what is sure is that, so here I've put the most simple models we have, of course, and we can generalize that a lot, actually, and to have like basically any kind of instruments possible that could also take into account maybe in some limiting regime and some approximation from the model of from their model to show that the connections between the two. But it's a work that we need to do still. But maybe that from what I've understood that we are not looking at what is the maximal probability. We are really looking at the law of the measurements. So maybe that with the specific instruments. But for sure, we need to, like it's an ongoing work, and we need to compare a bit more our result with us.
Okay, thank you. Then we thank Tristan again. And we can back on site.
This there. Yeah, okay.
The next speaker is Pavel Exner from the Doppler Institute in Prague, and they will talk about the discrete spectrum of soft quantum waveguides.
Okay, thanks, Gianluca. Thanks for the opportunity to, Thanks for the opportunity to speak here. So the title was announced, and what it will be about. There are various results about guided quantum dynamics, the relation between geometry and spectral properties. An elementary example is Dirichlet strip. If it is straight, fixed width, then of course the spectrum is absolutely continuous, trivial. But once we bend it, we will produce a discrete spectrum. This is used as a model of waveguides for particles, electromagnetic waveguides. There is a lot of literature. But as a model of, say, a semiconductor nanowire, it's not ideal in the sense that it does not allow to take the tunneling between different parts of the waveguide into account. So there is an alternative model which uses a Schrödinger operator with, well, okay, Schrödinger operator with a singular potential supported by a curve, as written here. And we have here a similar effect. If you take a curve which is bent, then we produce a discrete spectrum. Here is an example of such a result. We have a curve which satisfies its piecewise C1, satisfies this inequality, which means that there are no U-shapes, no self-crossings. And if it is asymptotically straight in the sense that this quantity here, which manifests the departure from the straight line, decays power-like, then it has the same essential spectrum as the straight line, but there is at least one eigenvalue below the continuum threshold. Now, if you think about that, of course, it is again an idealization because the width of this guide is 0. So a more realistic model would be what I would call soft waveguide, that is a potential ditch. And let me describe such a model. So again, I will start with the axis of the strip, which will be a planar curve, which will be infinite and smooth enough in order to have the curvature, the sign curvature, well defined. And I will assume that either it's C2 and it's curved only in a compact region, or it is asymptotically straight, but then I need to have it C4. And I will assume also again that the distance, if we go both ways along the curve, goes to infinity. Of course, the curvature is determining, because knowing the curvature, I can reconstruct the curve up to Euclidean transformations. And now the waveguide. So I built a strip along the curve of a fixed half is A, and I will assume that the strip does not intersect itself. And I will parameterize the strip. I can parameterize the strip by the natural curvy linear coordinates. One is the arc length of the curve, and the u is the perpendicular distance from the curve. And then the profile of my potential ditch will be potential which will be, say, L infinity, and supported in the interval minus AA. I assume that it is non-negative, but it's only for the convenience. On the other hand, it is important that it has a compact support. And I consider now a Schrödinger operator with a potential which is such a potential, which has a potential in form such a ditch, depending on the transverse variable given by this function v. Since the potential is bounded, of course, the domain is just the second Sobolev space. And I also need for comparison a one-dimensional Schrödinger operator with this potential v. So certainly such an operator has an isolated eigenvalue, and I will denote by epsilon 0 the ground state and phi 0 the corresponding eigenfunction. Now, the first question is about the essential spectrum. So it's not so difficult to check that the essential spectrum is the same as is the in the straight potential ditch, that it starts from the ground state of the transverse part of the operator. And I also can use the results I mentioned in the opening to get some existence result. For example, I know that the operator with a singular potential, with a delta potential, can be approximated by operators which have a scaled potential. This convergence is norm-resolvent 1. Therefore, the result I mentioned about the singular Schrödinger tells me that if I take a profile which is deep and narrow enough, that for small enough epsilon, such a potential ditch will have a bound state. this can be formulated as such a proposition. I will not go into details. I told you what is the contents. And similarly, the result about Dirichlet strips can tell you, because I again know that if I take a rectangular well and send the haze to infinity, I get a Dirichlet Laplacian. So if I have a rectangular ditch with, which is deep enough, then again the discrete spectrum exists. But certainly I want something better. So the method I will use will be a Biermann-Schwinger analysis, which is a standard one. That is, I take the two-dimensional green function sandwich between the square roots of the potential, and I have the usual Biermann-Schwinger result. That is the bound state of the original operator exists if and only if the Biermann-Schwinger operator has an eigenvalue 1. And of course, if I have the eigenfunction of the green Biermann-Schwinger operator, I can reconstruct the eigenfunction of the original simply integrating it with the green functions. Now, explicitly the Biermann-Schwinger kernel looks like that, where I know the green function of the two-dimensional Laplacian. And now I can use the curvilinear coordinates to find a unitary operator which maps the ditch, the curved ditch into a straight one. It's a simple transformation. Just I write it in terms of the coordinates S and U, but I have to remove the Jacobian. So that's a unitary equivalence. And the kernel then on a straight slip look as the previous one, but now the potential is replaced by an effective potential which contains is it visible? Yeah. Which contains the part which is given by the curvature. Now, in particular, when the strip is straight, then of course the Biermann-Schwinger kernel can be written explicitly, because in the longitudinal variable it's a convolution type, so you can rewrite it as a direct integral, and the fiber, not surprisingly, has this form, which is just the Biermann-Schwinger operator for the one-dimensional comparison operator. Okay, and now I can also write, knowing the ground state of the one-dimensional operator, I can write the function which is a generalized eigenfunction, which is at the bottom of the continuous spectrum. And now comes the main result, which is as follows. I construct such a functional. I take the function which is basically the difference between the curve and the straight one, and the discrete spectrum is non-empty, provided this integral of this thing is positive at the value which corresponds to the ground state of the transverse operator. Now this is already a result which criterion which is quantitative in contrast to the asymptotic results I had. Okay, so now not so much time for proofs. Just the proof is you have to prove that your Biermann-Schwinger operator has a spectrum which extends over the value 1 at kappa 0, at the threshold of the transverse operator, which you do variationally. You simply construct, you take a generalized function at the bottom and with a suitable modifier, and then you just treat the curvature as perturbation of the straight case. That is, you take the difference between the difference of the two Biermann-Schwinger operators, and if you write it properly, it's exactly the functional I gave you. Now you can derive various consequences. For example, if I take a class of profiles for which the infimum is below some fixed value, like that. Again, yeah, never mind. Then the claim is that the discrete spectrum is non-empty if the guide is narrow, enough. I skip again the argument, and instead of going into detail, because my time is coming to the end, a couple comments in closing. The criterion, as I said, is quantitative, but the drawback is that you have to calculate this complicated integral, and in particular cases it might not be easy. So with luck, a simple existence result, as I had in the cases I quoted at the beginning. The question, of course, is whether you instead cannot use a variational method not to apply it to the Biermann-Schwinger, but to the original Schrödinger operator. There, the trouble is that in order to construct the trial function, you cannot. It's difficult to do it in a sufficiently general case. There is a very recent result of these 3K orders who managed to do that, but at the expense of using quite particle shape, what people usually call book cover. And for this potential ditch, they proved the existence of bound states by a straight variational method. There are other results. For example, there is a result by Eger, Kerner, and Pankrashkin, because bending is not the only geometric perturbation. So they, for example, showed the existence of bound states in a cross structure of two such potential channels. And the last one, you may consider not only the infinite channels, but for example, if you take a channel which is as a form of the loop of a fixed width, fixed length, sorry, then you can prove that you ask about the optimizer of the ground state, and you can prove that the ground state is maximal if such a loop has a circular shape. And there are other results and many open questions, but my time is over. So I referred for all that to the paper I showed. And with that, thank you for your attention.
Thank you very much for the nice talk. Are there questions? Please, Doria.
Is it possible to exclude singular spectrum, singular continuous spectrum?
Singular spectrum, yes. Yes, that's to get a singular continuous under the assumption I have, that is the reasonable smoothness. You can prove. We have not done that, but I'm pretty sure that you can prove that the continuum has absolutely continuous character. What would be much more difficult is probably to in the infinite strips to exclude the existence of the embedded eigenvalues.
Other questions?
May I ask one?
Please, Svetlana.
Yeah, so is your theorem criterion and if and only if result, so that you say if integral is positive, then no, there is no empty discrete spectrum, so if it is not positive?
No, Svetlana, it is a sufficient condition, but a quantitative sufficient condition.
Quantitative, okay,
yes.
Thank you. Okay.
Okay, as the time is running quickly, I suggest to thank Pavel again. And now we switch online with a talk by Simon Larson from Caltech in Pasadena.
Okay, can you see everything okay?
Yeah, we can hear you.
Excellent.
Okay, so Simon Larson is going to talk about the Kronig-Penney model in a constant electric field. Please.
Thank you, Gianluca, and thank you, Svetlana, both for the opportunity to give a talk here. And what I'm going to talk about is contained in a fairly recent joint work with Rupert Frank, also at Caltech. And it concerns a certain family of one-dimensional Schrödinger operators, namely the following family. It depends on two real parameters, f and lambda. And it's just a simple Schrödinger operator on all of R with a potential that splits into two parts. First, we have a linear part of the potential. It's just a constant electric field. And we have a periodic part, which is given by this sum of Dirac deltas over the integer lattice. And that is coupled with strength lambda. And the questions we ask is simply, how do the spectral properties of these operators depend on the parameters f and lambda? Now, there are three sort of very simple cases here. And that's when either f or lambda or both are zero. Then we have either the Laplace operator, the Stark operator, or the classical Kronig-Penney model. In all three cases, we have only absolutely continuous spectrum, although the structure of the spectrum is rather different between the three different cases. It's purely absolutely continuous. Now, when neither f or lambda is zero, the picture is much more complicated. And there are, in fact, very few mathematically rigorous results concerning this. It was a fairly popular model in solid-state physics back in the 70s and 80s. And it was suggested, at least in work of Brezkovsky and of Chinikov in 76, and also Borisovich in 97, that you should see a transition from having a dense pure point spectrum on all of R to dense singular continuous spectrum, again, on all of R, depending on the sort of relative strength of the two parts of the potential in terms of f over lambda squared. Now, slightly later, Au in 90 and Buslaev independently in 99 suggest that this might not be the full picture and that there might also be sort of a number theoretic dependence on the parameter f. And what me and Rupert essentially show in this paper that I'm talking about is that this number theoretic behavior is really there. It's present. So what we show is that if our field strength is a rational multiple of pi squared, then in fact, you have absolutely continuous spectrum covering all of R. You have no singular continuous spectrum. You might have a number of eigenvalues, but we know the precise location of those eigenvalues. They are contained in some explicit lattice given in terms of f and lambda. So this is very different from the picture that the physicists believe to be true, that it should only depend on sort of the relative strength through f over lambda squared. But we do sort of believe that that is the case, at least generically. I would think that it's still the case if you just have an irrational multiple pi squared instead of a rational one, but it's far from clear so far. I also want to say that while this main spectral result that I'm displaying here is restricted to this rational case, a lot of the work that we put into proving this result actually works for general values of f. And we sort of reduce the model to a simpler system, or hopefully simpler, and that system we are able to understand under this rationality assumption. Okay, so one motivation for thinking that this transition from pure point to singular continuous is the sort of generic case comes from looking at a suitable random model. Namely, instead of having all the Diracs having the same coupling constant lambda, we replace the coupling constant at site n with independent random variables with mean 0 and fixed variance, and some suitable regularity assumptions, but I don't want to get into those details here. Now, this model was already studied in the 80s when all the physicists were looking at this. And De Leon, Simon, and Soyard wrote a very nice paper in 85 where they prove that for this random model, you have almost surely that the spectrum is all of R. And almost surely, if f over lambda squared is sufficiently large, then you only have continuous spectrum. And in comparison, if that quantity is small, you only have pure point spectrum. Now, they did not sort of show that there was a sharp transition or where that transition could be. And what we do now is to refine this result in precisely that direction. We show that there is indeed a sharp transition. It's located at f over lambda squared being 1/2 in the units we've chosen here. And we also show that the continuous spectrum that appears when f over lambda squared is larger than 1/2 is singular continuous and not absolutely continuous. I think De Leon, Simon, and Swihart could probably have proven that a year or two later, because Swihart wrote a paper on a similar topic, but it's stated to be open in their paper from '85. Okay, so I want to spend the rest of my time talking a bit about sort of the main ingredients that go into proving mostly the deterministic result. The random result is proved in a similar manner, so you will get the main ideas anyway. And hopefully I'll get to sort of give them slight motivation for why this number theory things appear. So the main ingredient, or one of the main ingredients in our proof, is the use of Gilbert-Pearson subordinacy theory. And that essentially reduces the characterization of the spectral nature of these operators to understanding the generalized eigenvalue equation and the asymptotic behavior of solutions of the generalized eigenvalue equation at a fixed energy. So from now on, I'm just going to talk about ODEs, essentially. So how do we study these ODEs? Well, we write them in a suitable set of coordinates, which we call relative preferred coordinates that have been around for a while. And we pass those coordinates by fixing a particular solution of the Stark equation at energy E and field strength F. So this is just the equation that we have without the Diracs. Now, there is a complex, nowhere vanishing solution to this equation, which can be written as e to the I gamma divided by gamma prime, square root of gamma prime for some suitable function gamma, which has the following asymptotic expansion. You do not have to remember all of this. It might be suitable to remember that gamma is essentially like x to the 3/2, and gamma prime is like x to the 1/2. But I'll probably remind you of that anyway. So with these functions in hand, we can write any solution to our true eigenvalue equation. So when we have the Diracs there, as a linear combination of this reference solution and its complex conjugate. And we study our problem in terms of studying, that linear combination is of course only valid on one interval between the Diracs. So we study our solutions by studying how these coefficients change when we go from one interval to the next. They satisfy a certain discrete recursion equation given in terms of the following matrix, which is just the identity, plus a bounded matrix depending on this phase gamma, and with a coupling constant that decays since gamma prime grows like a square root when n goes to infinity. The important part for Gilbert-Pearson theory is that we control the integrals of psi squared in terms of alpha squared, these coefficients. So we need to understand the asymptotics of alpha to understand the asymptotics of psi sufficiently well to do Gilbert-Pearson theory. Now, if you write these equations in sort of logarithmic polar coordinates and iterate the equation many steps, you get sort of the classical preferred coordinates. And you find that the absolute value of alpha n, which is what we're interested in when n goes to infinity, can be written as in terms of certain oscillatory sums. Namely, you have amplitudes that are essentially lambda over gamma prime and some oscillating factor whose oscillations are governed by linear combination of gamma and eta, where eta is the argument of alpha, this coefficient. And eta itself satisfies a similar equation. So essentially what the analysis boils down to is to try to understand exponential sums of this form. Namely that you have this amplitude to some suitable power. Since gamma grows like a square root, we only need to understand this up to power or power 3 or higher. This is trivially convergent and we don't need to understand more. Now if n is 1 or 2, then we're sort of in more trouble and we actually need to understand what the oscillations lead to in terms of cancellations and how these sums actually behave. Now, studying exponential sums is not a trivial subject, far from it. And even sort of without this unknown phase perturbation eta here, even without that, understanding the asymptotic behavior of these sums, as we did the index set going to all of Z, is very, very difficult. And in our case, we have these non-trivial perturbations, which cause quite a lot of trouble. But the way we can get around that is to show that on suitable scales, we can actually treat gamma or eta, sorry, perturbatively, and show that it does not affect the exponential sums too much. And from understanding the exponential sums to some degree in the rational case, we can go full circle and compute the asymptotic behavior of our generalized eigenfunctions. So all these number theoretic effects that we see can essentially be traced to these exponential sums and how gamma depends on this parameter f. And with that, I think I'm running out of time. So thank you very much for your attention.
Thank you very much for the nice talk and for being perfectly on time. And let me check if there are questions in the lecture hall. Please.
I'm wondering what's the condition on f will be if the lattice has an irrational constant.
Well, you can rescale everything here. So the rationality is really tied to that we're looking at the integer lattice. So it will be relative to the lattice spacing if we rescale.
All right, thank you.
Maybe there are questions online I forgot to ask before, but maybe Svetlana, you see if there are questions online?
Yeah, may I ask one? So what happens at exactly 1/2? What do you expect?
I would expect that it's almost surely singular continuous spectrum for the random model at this critical case. But I cannot prove it. And I only know of one result where they actually succeed in proving that, and that's a result by Minami from '92 with white noise instead of the Diracs.
So your expectation is only based on Minami or on something else?
Well, Minami and some computations that you can do in the style of Minami here as well.
Another question in the lecture hall? Please, David.
Yeah, maybe just a quick question. What happens if the locations are random?
That is a good question. Depends a bit on how random, but I would think if you do sort of a mean zero uniformly bounded variance perturbation of the lattice, that you would essentially be looking at the deterministic model again, or at least our analysis would not be able to pick up on any advantages of that randomness so far. So I think, unfortunately, you are led to the same exponential sums perturbed by something that's convergent and doesn't affect the problem. Unfortunately, it would have been a very nice model to study as well.
Okay, thank you.
So time is running quickly, so I suggest that we thank Simon again. And we have another online talk by Lingrui Ge from University of California in Irvine. Okay, see you. So. Try the voice. Can you unmute? Yeah, perfect.
Yeah, can you hear me?
And so Lingrui Ge is going to talk about quantitative almost reducibility and its applications. Please.
Okay, thank you for the introduction. I'd also like to thank the organizers for the invitation. Today I will talk about quantitative almost reducibility and its applications. And this is based on joint works with Kachkovsky, Yu, and Zhou. First, let me introduce some concepts. So the one-frequency quasi-periodic Schrödinger equation, Schrödinger operators, and Schrödinger cycles. First, let's introduce the Schrödinger equation. It is given by this guy. Here, H theta is the Schrödinger operator. So this is the operator. And this is a quasi-periodic operator in the sense that the potential here is a negative function, and we have a frequency alpha. This is an irrational number. So the potential is generated by a function on some orbit. And for the Schrödinger operator, we can define one quantity called the Schrödinger cocycle. It is a pair. The first one is the frequency. The second one is a 2x2 matrix. So of this form. And these three objects are closely related in the following sense. First, there's a relation between the time-dependent Schrödinger equation and the Schrödinger operator. It is called the famous Rage theorem. That is, if you give your initial data, if you consider the evolution of the time-dependent Schrödinger equation, you consider this HS norm. This is closely related to the spectral decomposition of the spectrum measure G mu phi. This spectrum measure is defined by this Schrödinger operator and this initial data. So this is the first relation. The second relation suggests that there is a relation between the Schrödinger operator and the Schrödinger cocycle. That is the subordinate theory. It says the spectral decomposition of the spectrum measure of this measure. This is closely related to the growth of the norm of the iteration of the Schrödinger cocycles. And from these two relations, you can see if you want to study the the evolution of the time-dependent Schrödinger equation, you can reduce this problem to study of the growth of the norm of the iteration of Schrödinger cocycles. And today, our main aim is to introduce a dynamical system approach to study Schrödinger cocycles and use it to study the spectral theory of quasi-periodic Schrödinger operators and the evolution of time-dependent Schrödinger equation. Okay, since I have said the spectral theory of quasi-periodic Schrödinger operators is closely related to the growth of the norm of the iteration of Schrödinger cocycles. So now let's first define this iteration. This is called the transfer matrix. And based on the growth of the norm of this transfer matrix, one can divide the spectral set. This is the spectral set of the Schrödinger operator into three regions. The first region is the supercritical region. That is, if the supremum of this norm, the norm of this transfer matrix grows exponentially. That is, for this guy, it grows very fast. And the second region is the subcritical region. The subcritical region says if the norm of this transfer matrix grows sub-exponentially in some band. Here, since this matrix A is analytic, so you can consider the complex extension of this matrix. It says if you can find some small band such that the norm of this transfer matrix grows sub-exponentially in this band, then this is subcritical. it grows something, it is rather slow. And otherwise, we call the region the critical ones. So why we divide the spectral set into these three regions? Because different regions are treated by different techniques. For example, the subcritical region is treated by the almost reducibility theory. And the critical region is rare in the sense that it is of zero Lebesgue measure. This is proved by the renormalization theory. And the supercritical region is sometimes treated by the large deviation theory and the multi-scale analysis. And the different regions display different spectral phenomena. And today, the tool we introduced today is called quantitative almost reducibility. It is a powerful tool to study the subcritical cocycles, to study this region. And now let's introduce what is reducibility and what is almost reducibility. Reducibility says you have an analytic map such that the original matrix, this A, is conjugated to a constant matrix. So this is reducibility. Almost reducibility says you can find a sequence of matrix Bn and a sequence of error Fn such that the original matrix is conjugated closer and closer to a constant matrix. And here, this error will converges to zero analytically. So it is obvious that almost reducibility contains reducibility, so it is a weaker concept. And for quantitative almost reducibility, it says you have quantitative estimates on this Bn and this Fn and this An. So you have a very special form of the conjugations Bn. It can be written into three parts. The middle one is a rotation. The last one is a matrix that is close to the identity. And you have a special form of the, also have a special form of the constants. So it can be written in this form. And moreover, you have very good estimates on all the objects above. For example, you will have a sub-exponential growth of the analytic norm of this Bn theta. And you will have exponential decay of this mu n. And you will have super exponential decay of this yn and the error Fn. And for almost reducibility, there is a famous conjecture called the almost reducibility conjecture. This was announced by Avila. It says that for any irrational number, when you consider this cocycle, and it is subcritical if and only if it is almost reducible. This is also why we said almost reducibility is a powerful tool to study subcritical cocycles, because in some sense they are equivalent. But in the above theorem, the estimates of the conjugations and the constants are not good enough to get some nice spectral applications. For some nice spectral applications, we need the following one. For the following one, we assume this frequency is Stephantin. This is some arithmetic description of this frequency. It is a 4 Lebesgue set. And if alpha is Stephantin, then we can prove this cocycle is subcritical if and only if it is quantitative almost reducible. So we can give a quantitative estimates of all the objects in the almost reducibility. And this kind of quantitative almost reducibility will enable us to achieve several sharp spectral results, which cannot be got just from almost reducibility. For our applications, we will formulate a result for the almost massive orbiter, which is the central model in the quasi-periodic models. And for this model, we take V equals to 2 cosine 2 pi theta. It is the simplest even analytic function. And this orbiter you can find, by the definition, you can find that this orbiter is subcritical if and only if this lambda is smaller than 1. It is supercritical if and only if lambda is larger than 1. And there's the famous result for this orbiter. called the metal-insulator transition, proved by Jetmiskaya. She proved that if alpha is 17, then we have, if lambda is smaller than 1, this orbit has purely absolute continuous spectrum for almost every theta. And if lambda is larger than 1, this orbit has Anderson localization for almost every theta. So what can we say? This is some result for the operator. So can we use this result to get some result for the almost Marcelli equation? So this is operator, and we want to get some result for the almost Marcelli equation. And the quantitative, this is not a corollary as this result. We need more quantitative estimates. For example, why quantitative almost reducibility plays a role? Because on the AC spectrum part, it will give more information on the generalized eigenfunctions, which is enough to prove something more than just AC spectrum. It is enough to prove ballistic motion for the almost Marcelli equation. And moreover, there's a relation between reducibility and localization. So if the subcritical cocycle is reducible to some constant matrix, then its dual orbiter will have exponentially decaying eigenfunction. So quantitative almost reducibility will also give more information on its dual eigenfunctions, which is enough to prove something more than pure point spectrum, to prove some result, something like exponential dynamical localization. Now let's give the definition of ballistic motion and exponential dynamical localization. But ballistic motion says, if you consider the HS norm of this time evolution of this time dependent Schrödinger almost Marcelli equation, if it has a lower bound, has such a lower bound, we say this orbit has a ballistic motion. Moreover, if this limit exists and equal to some number, we call this number the ballistic motion velocity. And another phenomenon is called exponential dynamical localization in expectation. If we consider the integral of this evolution here, if it has exponential upper bound, we call this operator has exponential dynamical localization. It says when t goes to infinity, it will never grow. This one says when t goes to infinity, it will grow to infinity. And we can also define exponential decay rate in expectation in this sense. And quantitative almost reducibility will enable us to give a sharp transition for the almost Marcelli equation. So the previous result is for almost Marcelli operator. Here is for almost Marcelli equation. For almost Marcelli equation, if alpha is 17, we can prove that if the lambda is smaller than 1, then for any theta, this operator has ballistic motion with ballistic motion velocity equals to this guy. This function G is defined by this equation. Here, N is the density of states. And this is the first result is a joint work with Kachkowski. And if lambda is larger than 1, we can prove that the almost Marcelli orbiter has exponential dynamical localization in expectation with exponential decay rate, log lambda. And this is a joint work with Yu and Zhou. And this gives a transition for the almost Marcelli equation. I'd like to say these two results are not a corollary of AC spectrum or pure point spectrum. We need more dedicated estimates on the general eigenfunctions or eigenfunctions to get these two results. And the second result was also proved by Jetmiskaya, Krug, and Liu. I think I have run out of time. Thank you for your attention.
Thank you for the nice talk. Are there questions in the lecture hall? Perhaps there are questions online?
Yeah. May I ask one?
Yes, please.
Yeah. Yeah. Okay. So in this last two theorems, so these are stronger results than, as you mentioned, the AC spectrum and pure point spectrum, naturally. So do you expect a regime where these results, for example, the first result does not hold yet?
Yeah. I think if alpha is very Liouvillean, then the first result does not hold. I think this limit does not exist.
Does not exist.
Yeah.
Okay. And do you expect some arithmetic threshold for this?
Yeah.
Because we always have AC spectrum without the Diophantine condition in this regime, right? Yeah.
I think there is a tradition, something like if lambda is smaller than E2 beta, beta is the Liouvillean exponent. Something like if four major reducibility holds, then this result hold. Otherwise, it does not hold. Something.
So you expect a sharp transition, so it holds up to the beta, and otherwise the limit simply does not exist.
Yeah. Otherwise, the limit does not exist. Something, it is slower than T2S. Something, it is slower than this one.
Okay. All right. Thank you.
Thank you. Yeah.
Okay, then I suggest that we thank Lingrui again. And we switch again to the on-site modus. So our next speaker is Giovanna Marcelli from SISSA in Trieste, and she will talk about a new approach to transport coefficients in the quantum spin-Hall effect.
Thank you. First of all, I would like to thank the organizers. I am really grateful to have this opportunity to give a talk, and also to the audience, so the people that are still here on site and online. So my seminar is based on this joint work with Gianluca Panati and Stefan Teufel. The main goal of this work is to shed some light on the theory of spin transport in gapped non-interacting fermionic system with application for the quantum spin-Hall effect, since the spin transport theory is still in a preliminary stage as compared to the one for the charge. To reach the main goal, we set an intermediate one, which consists of establishing a new paradigm for quantum transport theory, especially related to the linear response theory. This will be reached by the construction of non-equilibrium almost stationary states. Since the standard cube formula becomes cumbersome and intractable for spin transport. As a byproduct of this work, we will recover results for charge transport in this framework, so with application for the quantum Hall effect. So, as I said before, now we focus on the intermediate goal. So, what does it mean, linear response formalism? In the context of Hamiltonian quantum system, it answers to the following questions. If we denote by rho epsilon the state of the system after the perturbation has been turned on, what is the change of the expectation value of an observable A caused by a perturbation epsilon V at the leading order in its strength epsilon, where epsilon is a small parameter? So, we have as an input the triple H0, which is the unperturbed Hamiltonian, pi naught, which is its equilibrium states, and epsilon times V, which is the perturbation. And as an output, we want to compute sigma A, which is defined as the term carrying the linear coefficient in epsilon of this difference that you see at the left-hand side. is the difference between the expectation value of A in the perturbed state minus the expectation value of A in the equilibrium state. These expectation values are computed via suitable functional. In this case, will be the trace per unit volume. And of course, we are interested in the real part. We call sigma A the conductivity of A. How do we model the switching process? So we start with an Hamiltonian H0, and then we want to turn on, in this case, a constant electric field, let's say in the J direction. And we want to switch on by this function f, which interpolates between 0 and 1. So for positive time, the perturbation is fully turned on. But the switching we want to do adiabatically, so we also add an adiabatic parameter, in this case, eta. So notice that xj here is a linear potential and is just the position operator in the jth direction. We denote by ρt the solution of the following Cauchy problem. So the first line is just the Liouville equation associated to the perturbed Hamiltonian, and then we set the state in the equilibrium when the perturbation is fully switched off. So now the Neas approach circumnavigates the standard time adiabatic perturbation method, which we will lead to the Kubo formula, and is constructed in such a way that we can compute, so you can read this in this inequality, the expectation value of an observable A in the state when the perturbation is completely switched on, so for positive time, just by computing its expectation value in the Neas. This up to error epsilon squared, and this uniformly in the adiabatic parameter. This can be done also for a higher order in epsilon, but since we are interested in the linear response, epsilon squared for our purposes will be enough. Here there are some selected references where the linear response is proved. And the Neas in particular is adopted in this series of work of Monaco-Teufel, and Haneijk-Teufel, where also the thermodynamic limit is proved. Okay, now we assume that this inequality holds, and we just want to focus our attention to compute the formula for the spin conductivity. So we just have to introduce the definition of the spin current. Okay, so which is our mathematical framework? The Hilbert space is L2 of Cal-X tensor product with C to the n, where n is the number of the internal degrees of freedom of the particle. Cal-X can be R to the D or a discrete d-dimensional crystal. The unperturbed Hamiltonian H0 is assumed to be a periodic gap operator and bounded from below, satisfying some technical but mild hypotheses. The key assumption is the spectral gap, and we fix the Fermi energy in the spectral gap, defining the associated Fermi projection pi naught. Then the construction of the Neas is as follows. So pi epsilon is the unitarily conjugated of pi naught, so the equilibrium state, where this unitary is e to the I epsilon s, where s is a self-adjoint bounded and periodic operator. By just expanding in epsilon this operator, we will obtain the right-hand side. So let me focus on the linear term, so where we have epsilon times pi 1, where pi 1 is defined as the inverse Liouvillean of the commutator between xj, which is related to the perturbation, and the pi naught, namely the Fermi projection. The inverse Liouvillean is defined by the last line you see on the slide for any off-diagonal operator, where off-diagonal with respect to pi naught. Now we are in shape to give formulas for the conductivity of unobservable A. So just I recalled at the first line the definition of sigma A, then assuming that the inequality I showed to you before on the Neas holds true, and expanding the Neas in epsilon power, we get the second line. Thus, we have that the conductivity of A is the real part of the trace per unit volume of A times pi 1. Now we have just to specify A. So we are interested in the spin current. There are two definitions in literature. So capital S is the identity on the first factor of the Hilbert space. Tensor, let me just focus on SZ, so the third component of the spin. The conventional spin current is defined, roughly speaking, as SZ times the velocity operator, and then you symmetrized. Instead, the proper spin current is defined up to Ni as a total commutator between H0 and Sz times Xi. Of course, these two definitions are equal if H0 commutes with the spin. Instead, when H0 does not commute with the spin, namely the spin is not conserved, an ambiguity arises. Now we want to investigate this case. So we have that if we define accordingly to these two spin currents the respective conductivity, we will have this relation. So the proper spin conductivity equals the conventional spin conductivity plus a rotational spin conductivity, where the conventional part is given by these two lines formula, and the rotational part is given by this trace per unit volume, where let me stress that there is xi times this operator that trace the fact that the spin is not commuting with the Hamiltonian. The proof just used the fact we can split the proper spin current in these two terms. The first one, which is related to one term of the conventional one, and the second one that will be the cause of the presence of the rotational part. Also, to guarantee that this rotational term is well defined, we need to show that the trace per unit volume of the operator that is at the left-hand side of close to xi has a trace per unit volume vanishing. Okay, now we would like to have a deeper understanding of these formulas from the physical viewpoint. So we formulate the unit cell consistency. We say that any formula for spin transport should satisfy the unit cell consistency, namely that any prediction on macroscopic transport must be independent of the choice of the fundamental cell. These are just some examples of unit fundamental cell in the case of the honeycomb structure, for example, for the Chemili model. Just observing that if we take two fundamental unit cells, we can cut one into pieces, such that if you translate through a suitable lattice vector and you reassemble it, you will obtain the other unit cell. With this observation, we are in shape to find a sufficient condition, namely this sharp equation, where we have the operator that was close to xi in the rotational term of the conductivity, that if this operator restricted to each pieces of the unit cell as trace vanishing, then we have that both conductivity satisfy unit cell consistency. And moreover, in discrete models, the two conductivity agrees. So this shows that at the level of the conductivity, the choice between the two currents is immaterial as far this hypothesis sharp and discrete models hold. Remarkably, Che-Meili model is in this class. Okay, now there is also the much simpler case in which H0 commutes with the spin. So at the operator level, the two spin currents agree. So also at the expectation value level, they will agree. And they are given by this just one term, this trace per unit volume, that can be also rewritten in terms of a K integral. If we are in a two-dimension, since H0 commutes with the spin, we can also split P0 respect to this decomposition induced by the eigenspaces of Sz. And then we have that plugging this splitting in the above formula, we have that the spin conductivity is this difference, where the first term is 1/2 of the Chern number related to P0 up, minus the other one related to P0 down. So is the spin Chern number of P0. So this is our definition, which is, of course, in agreement with other works, for example, by Prodan and Schulz-Baldes. Now we have also a perturbative result when the S is approximately conserved. So if H0, which commutes with the spin, is then perturbed by adding lambda H1, where H1 a priori does not commute with the spin and satisfies some regular assumption and does not close the gap of H0, then we can say that the proper spin conductivity agrees with the conventional spin conductivity up to error order lambda, which agrees to the spin Chern number, which is an integer up to, is 1/2 of integer up to error linear in lambda. These results complements the robustness of edge spin currents proved by Schulz-Baldes and agree with the numerical simulation by Monaco and Ulsakar for these two time reversal symmetric models, where actually the correction terms scales quadratically in lambda. This is all I wanted to say. Thank you for your attention.
Thank you very much. Are there questions? Please.
I have a question about this UCC.
Yeah.
You said, I think, that the Che-Meili model satisfies UCC. So do you have an example of a model which does not satisfy?
For example, I mean, a priori, if this sharp condition doesn't hold, this equality between the two spin conductivity is not true. And I am quite sure that also in the paper by Domenico and Ulsakar, they have an explicit discrete model in which does not hold true.
Equally, if I may comment, there are papers in the physics literature which don't. And few ones, but no. Other questions? Okay, then we thank Giovanna again. We switch again to the online modus with our next speaker. So it's Rui Han from Louisiana State University in Baton Rouge. Can you hear me?
Yes, can you hear me?
Yes, perfect.
Okay, let me enter the full screen. All right.
So Rui Han is going to talk about Cantor spectrum of graphene models in magnetic fields. Please.
Okay, thank you for the introduction, and also thank the organizers for the invitation. So I'm going to talk about the works that are based on joint works with Simon Becker and Svetlana Chitmerskaya. So what is a graphene? Graphene is a two-dimensional material and with carbon atoms sitting on the vertices of a hexagonal lattice. So today I will first talk about the tight-bending models of graphene. So let's take a hexagonal lattice. And so this is the fundamental domain of the hexagonal lattice. And in each fundamental domain, there is a red vertex and there is a blue vertex. And so let's call it Mn. Mn indicates the location of the domain, and A indicates the red vertex, and B indicates the blue vertex. Then, so first let's talk about the non-magnetic case. So let's take a non-magnetic Schrödinger Laplacian tight-bending model. Okay, so it hops to the three neighbors. So M and B will hop to the three neighbors, which are all A vertices. And if you start with the A vertex, then it hops to the three B neighbors. Okay, so this is a model, non-magnetic model. And then the spectrum is very simple. One can easily compute. The spectrum is from -3 to 3. It's an interval. And then what if we incorporate a magnetic field? So suppose we have a magnetic field which is transversal, perpendicular to the lattice, and with the flux alpha. Alpha is a flux of the magnetic field in each hexagonal structure, in each honeycomb cell. Okay, and then this operator can be written as follows by choosing a standard Landau gauge. Now there is a magnetic contribution. So flux alpha enters here, is exponential, and also enters here. So the question is, what does the spectrum look like after we incorporate this magnetic field? Well, it turns out the spectrum gets really complicated. So this is a plot of the spectrum for many alphas. So how do we read this? How do we take a look at this plot? Horizontally is the energy. Horizontally is energy. Vertically, that's a flux, alpha. It is our alpha. So for example, when alpha equals 0, the non-magnetic case, the spectrum is from -3 to 3. It's an interval. And for example, the black part indicates the spectrum, and the white part indicates the complement of the spectrum. So for alpha equals, say, 1/3, then the spectrum actually consists of 6 intervals, 6 spectral bands. Okay. But let's suppose we are looking at a rational number. So let's take a slice here. And then it looks like there are gaps everywhere in the spectrum. It has holes everywhere. So it appears that for irrational alpha, the spectrum appears to be a Cantor set. Okay? And that is our main result. First, also, this picture is from the paper Helfer, Cadell, Letelier. And in their paper, they studied the rational alpha. So for alpha equals P over Q, they derived a Chambers step formula for the tight-bending model, and they also showed that the spectrum is a union of spectral bands. Our results with Becker and Chitmerskaya concerns mainly the irrational alpha. So we showed that for any irrational alpha, the spectrum is really a Cantor set. Further, it has a big measure 0. So this confirms our observation from the picture that has holes everywhere. And we also showed that for irrational alpha, the spectrum is purely singular continuous. And for rational alpha, for rational flux, we also have an estimate on the Lebesgue measure of the spectrum. So we showed that the spectrum for rational with denominator Q, it decays like 1 over root Q. And this result plus a continuity argument implies that for generic alpha, the Hausdorff dimension of the spectrum is less or equal to 1/2. So the spectrum has a fractal feature. And later, this generic alpha was improved by Sofsky to all irrational alpha. So this is the Ted-Benny model, and our result also can be applied to the quantum graph model. What is a quantum graph model? So here again, we take the lattice, the hexagonal lattice, but now instead of the hopping model between the vertices, we place a one-dimensional Schrödinger operator on the edges. So on each edge, we place a 1D continuous Schrödinger operator. Okay. So this is a quantum graph model. This is a non-magnetic quantum graph model. And then we can also incorporate the flux, magnetic fields in this model. And we also impose a Neumann boundary condition. Okay. One can consider more general boundary conditions, but in our paper, we only consider the Neumann boundary condition. Okay. So for the quantum graph model with magnetic field, we call it H2 the alpha. And at the same time, in order to present the results, let's also call the one with Dirichlet boundary condition, we call it H2 the D. Okay. So for the quantum graph model, we also have a full spectral analysis. So we showed that the quantum graph model, the point spectrum comes from the Dirichlet eigenvalues for any alpha. And this continuous part of the spectrum, we showed that is an unbounded counter set of Lebesgue measure 0 for any irrational alpha. And we also showed it's purely singular continuous. And the point spectrum and the continuous spectrum are away from each other. So in the sense, their intersection is empty. And we also have the Hausdorff dimension result. And we have a characterization of the eigenspace associated to each Dirichlet eigenvalue. So this is our result for the quantum graph model. And so far we have talked about the single monolayer graphene models. And one can also consider multi-layer graphene models. For example, the AA stack bilayer graphene model. So AA stack means you have 2 layers of graphene where the second layer is placed exactly on the top of the first layer, okay, with no shift or rotation. So that's the simplest example of bilayer graphene. So it has sectional structure. And for the AA layer bilayer graphene model, and this plot was generated in this paper. And it appears that there is a similar fractal structure of the spectrum. Okay. And it also appears that there is a counter set if one takes irrational flux. So if we look at this vertical slice, there are holes everywhere. And this is a recent result. So we are able to show that for the AA stack model, it really has counter spectrum, okay, for any irrational alpha and for any non-zero interlayer hopping. Let me take a look at the time. I have 4 more minutes. Okay, now let me just quickly talk about the ideas behind the proof for the monolayer model.
You have 4 minutes, but including questions. So it's correct you have 4 minutes, but if you want questions, save the last minute for that.
Yeah, 2 minutes. Okay. So if we take the titanium magnetic Laplacian on the single layer graphene, and then we can step by step we can eventually reduce this 2-dimensional model on the hexagonal lattice. We can reduce it to through a series of reductions. We can eventually reduce it to a Jacobi matrix on Z, so 1-dimensional operator. So here we should note, so here is the Jacobi matrix. And here we should note that the coefficient, the off-diagonal sampling functions is 1 plus e to the 2 pi I, blah, blah, blah. This sampling function is actually, the range contains 0. So this can be equal to 0 sometimes for certain theta. So such kind of Jacobi matrix are called singular Jacobi matrix. Okay. And then our analysis is really about this singular Jacobi matrix. And of course, when talking about the Cantor spectrum, one should naturally compare it to the almost massive operator, which Lingrui already talked about in his talk. So this is almost massive operator, where Cantor spectrum was proved for all parameters. And here in the almost massive operator, note that the off-diagonal sampling function are 1, constant 1, so it's regular instead of singular. And actually, a lot of techniques developed to study the Cantor spectrum of almost massive operator rely on the fact that it's non-singular. So for example, Avila-Krikorin result, Chitmerskaya-Avila's result, they rely on the non-singular, but here in our case, it's singular. So at first, it appears that there's a serious technical difficulty. But in the end, we found out actually singularity is on our side. It's good for our study. So we are able to explore the singularity in the following ways. And eventually, for example, we use singularity to show that there is no AC spectrum. And then combining with Potanyi theory and the zero Lyapunov exponent, one can just get Cantor spectrum for all irrational alpha. And also using singularity, we are also able to have a very clean and simple proof of the big measure of the spectrum, and which plus continuity implies Hausdorff dimension. And the recent result by Jittermanskaya-Krasovsky, they also use singularity to improve the modulus of continuity. Okay. So singularity is really on our side. And I think I will stop here, for questions.
Thank you very much. Are there questions? Okay, first there, and then.
I'm wondering that your result is also true for any material which has this hexagonal lattice.
Yes, I didn't quite hear. I didn't hear clearly the question. Sorry.
I guess your result is also true for any material that has this hexagonal lattice.
Yes, the underlying lattice is hexagonal. Is crucial. Yeah, it's bipartite. The fact that it's bipartite is crucial. Yeah.
Do you know if this one can extend these results for other lattices or?
Yes, there are. Yeah, that's a very good question. Actually, these results we can prove similar result for the Des lattice, and also the Lieb lattice. But I didn't include them here because the time, yeah.
Okay, then there was a question by Marius.
Hi, Rui. I wanted to know what you do different for the bilayer. Do you also reduce it to a 1D model that's maybe matrix valued?
Yeah, for the AA, thank you for the question. So for the AA bilayer, yeah, there is a reduction from the bilayer to the single layer and then eventually to the Jacobi matrix. Yes. For AB, and I'm still working on it. Yeah. I'm still working on to find a reduction. Yeah.
Okay, thanks.
Then I suggest that we thank our speaker again. And we continue with the last speaker of this session. It's Simon Becker from University of Cambridge.
Okay, perfect. Yes.
Okay,
thank you very much.
Hear you. So Simon Becker is going to talk about the Dirac equation as the core of topological insulators. Please.
Yeah, thank you very much for having me and for still being around at this time. Yeah, so this is joint work with Guillaume Ball, Alexis Drou, Clotilde Farmanian-Camera, Jian-Fang Lu, and Alex Watson. So our idea is that we want to have sort of an analyst perspective on topological insulators. Usually when people discuss this, they talk about Bike edge correspondence, and the tools that people use are often operator algebra methods. And so we want to understand the effect of topological insulators for sort of one very canonical model, as we think. Okay, so let me start by explaining our idea for how we model a metal or an insulator. So we think of the following situation that we have a periodic material. So this one will have bands, and so these bands can either, let's say, touch at a conical point, or they have a gap, like in this case. And a very obvious way to model this is just using a two-dimensional Dirac operator, where this parameter delta here, so if delta is strictly positive, then it models the gap, and if delta is equal to 0, then we have just these Dirac cones, right? So this the effect of delta just tells you whether close to 0 energy you have an insulator or a conducting material. Okay, so what is now a topological insulator, actually? So a topological insulator is a material that is sort of consists of two things, a bulk and an edge. And it is insulating in the bulk, and it's conducting on an edge. Okay, so this would not sound very fancy at the moment if there wasn't something crucial about this edge current. And that's that this current is sort of stable in a certain sense. So stable means here that usually when you have a material and it's a conductor, let's say a metal, then you have electrons that move in that direction, you have electrons that move in the other direction. And then when you apply a current or apply a voltage, then you produce a lot of heat. And the idea about these topological insulators is that, what is the main property here is that this doesn't really happen. So this current, it has a natural direction of propagation, and so you get much more stable currents. And so that's what we basically want to understand using our simple model. And what is the model that we want to use? So we want to understand edges. So this black line here is the edge. And this is the bulk outside, and we want to use as our model this simple Dirac equation here, and we want to understand how do these currents propagate along the edge when our interface or our edge here is weakly curved. So our assumption is that the curvature is weak, and we want to understand the effect of curvature on these topological insulators. Okay, so this weak curvature you don't see it in this scaling. So this is the semi-classical scaling. If you would put the epsilon into this kappa, which models the edge, so the zero set of kappa is our interface here. Okay, that's the edge. And so when this is equal to 0, you have a conductor. So that's why you have a current, a conducting edge. And if you're in the bulk, so if you're away from where kappa is equal to 0, then you have an insulator by the previous slide, because then you have something non-trivial on the diagonal here. Okay, so this is a very canonical model for the topological insulator, which is then a conductor when kappa is equal to 0 on the edge, and an insulator when kappa is not equal to 0 in the bulk. And now we want to understand these modes. So let us consider the straight interface. So that's a case that you can solve explicitly. So this kappa, it's just one direction. So this edge just points in one direction. So this direction is given by a vector v theta here. And the Hamiltonian accordingly is this. So this kappa, you can work out what it has to be in this case. And so a simple calculation just shows that in this case, a wave packet that has sort of Gaussian decay away from the edge. So you have something that decays quadratically in the exponent. It stays like that under time evolution. So this is the time evolved state. And you just have a propagation along the edge. Okay, so this r theta, it rotates you in the direction of the edge. In the direction orthogonal to the edge, you have Gaussian decay all the time. And along the edge, you just propagate, have just a uniform propagation. And so this is the solution to the Dirac equation. And so this is what everyone would expect for a topological insulator. So maybe I should say, I'm now considering a wave packet that starts at the edge and stays on the edge. What happens away from the edge? So there, mathematically, you don't really have to do anything new, because that is sort of classical semi-classical theory, classical semi-classical theory, so to say. So if you have a Hamiltonian and you have that as your symbol, so that's the one we're considering. So then you have that set of the edge that we are looking at. So psi is equal to 0 and kappa is equal to 0. And the eigenvalues of the symbol of H, they are just given by that. And so if you start from your initial state is not semi-classical localized on the edge, so this condition doesn't hold, then the time evolution is just given by the Hamilton equations to leading order. Okay, so your wave packet would just propagate according to what classical mechanics tells you, where this is the Hamilton function, which is just the eigenvalue of your symbol. And so you would also never reach the edge, because you have, of course, energy conservation. So anything that sort of starts away from the edge will also not become an edge state eventually. Okay, so now what is the theorem? So the theorem in a sort of simplified manner says that you start with a Gaussian initial state. Okay, so that's again something like this, that is sort of quadratically exponentially localized away from the edge. And then under time evolution, it will stay such a state on the edge, and it will propagate along the edge. Okay, so you have this yt, that's sort of a parameterization of your edge here. You know, your state gets sort of shifted by this yt. And then you do this up to an arrow that is, well, it depends on epsilon. So how localized your initial state is, that's because we have a sort of semi-classical result, which assumes that you have weak curvature, and it depends linearly on time. Okay, and so that is our result, that if you start with a state that is localized on the edge, and it has the right initial condition, then it will stay on the edge and it will move in one direction. Okay, let me try to illustrate this. So this is an example of the edge. So this is the light blue profile here that you see. And then we have an initial state that is localized here. So it's this yellow dot that you see here. What I've taken now are sort of snapshots where I look at the time evolution. So this is numerically solving the Dirac equation. And then I don't know, every, let's say 0.5 seconds, I look, what is the shape of my profile? Okay, so I start with my right initial state that my theorem gives me. And then you see it just propagates and it almost doesn't change along this interface. So now you could ask, okay, so what's so special about this initial state here? Well, you could try to take, for example, the orthogonal complement of this vector here. If you take the orthogonal complement, then you see that this state, it will not move at all. It will not move in the opposite direction. It tries to move in the opposite direction. But this is the point of these topological insulators, that you're sort of not allowed to move in the opposite direction. So what happens is that your state just disperses, okay? And that's sort of the main idea of these topological insulators, that there's a preferred direction in which these edge states propagate, okay? And so if you take the linear combination of those, you will see some part that propagates along the edge and the other one just disperses. And so because it's already a bit late, so I'll try to illustrate this now in sort of many examples. So if you have your edge, and your edge has, of course, there's the zero set, which is sort of which defines in our case where the edge is. And if that gradient, so if the edge becomes very flat, then what happens is that, okay, your state starts here, your edge state. And then if you're basically confined to an edge. So if that edge becomes flatter and flatter, then what happens is that your wave packet sort of spreads out. That's what you see here. And now you confine again, and then your edge state actually recovers again, and you basically get again this nice localized Gaussian profile. Another effect that is sort of very crucial and that I'm not really exhibiting here in this error bound to sort of keep it simple is that this depends a lot on curvature. So curvature is the enemy of the edge state. So when you had, for example, this linear profile, the straight edge, then I showed you that the Gaussian profile is preserved for all times. So if you have now something like a circle, you start with your edge state here, you let it propagate once around the circle. Then you see that here, the edge state has already dispersed quite well. I mean, it still looks like, a sort of very localized state. But if you compare this one, the initial state, to the state that you get when you once propagate around, then this one has dispersed already in a substantial manner. Okay. Another thing that happens for this edge state is that, and there you see that this is not at all classical motion, that if you have an incoming wave packet and it propagates up to such a crossing point where this is your edge, this light blue thing, and this is also your edge. And now if you have an incoming wave packet, then what happens once you hit these kind of intersection points is that there's a scattering process. So if this was, I don't know, classical mechanics and you had a ball that would, roll in here, okay, it would either continue here or it would continue there. So quantum mechanics works very differently. So you have a sort of scattering process that tells you there's, one direction in which you can go and you cannot go on the other one. So either you backscatter along this one or you propagate along this one. But this edge doesn't move, for example, in that direction. So these are sort of the subtleties of edge states and these preferred directions. So now, let me sort of tell you something about what happens if you include a magnetic field. Of course, you cannot do this magnetic field. You cannot take a very strong one because otherwise the Lorentz force will just, move your particle away from the edge. So you also have to make that sort of slowly varying that magnetic field so that it doesn't really, the vector potential is slowly varying, which means that the magnetic field is sort of small. And so it doesn't, move your edge state away from the edge. Okay, there's a similar theorem that we have. I just don't try to show it in order to save some time and make it a bit more relaxing to just look at some plots, what happens. One thing that happens immediately for these edge states in magnetic fields that you see is that, that once you put a particle in a magnetic field, and it's localized on the edge, so it's the right edge state, the motion will become smaller. So this one that you see here, which propagates the furthest, so these are the initial conditions. This is my initial edge state. This one that propagates, furthest away, that's the one in zero magnetic field. And if you have, so this is positive magnetic field in that direction, this is negative magnetic field. So if you go to a strong positive magnetic field, then the speed of your edge state will just reduce. And this is actually something we, I think, did not know before that this happened. And so far, I think we also did not find a proper reference in the physics literature that explained this to us, at least. Another thing is that you see once you have a non-constant magnetic field, you see some strong dispersion effects, okay? So we have a constant magnetic field, and then we have one that varies sort of, a sort of varying term, okay? And then we see that the amplitude of your edge state will just decay according to some inverse power law. So sort of varying magnetic fields, okay, if they are constant, then the amplitude is sort of preserved similar to before, but if they are varying, then that's sort of the enemy of the edge state. But this is not, so it's not true that, for example, once you have a very strong magnetic field, okay, once it's very strong that the Lorentz force kicks in, then of course your edge state will not be preserved. But what happens is that if you have just a homogeneous magnetic field, then our result shows that this is actually not a perturbative effect, that, okay, without a magnetic field, everything is perfect. And once you switch on the magnetic field, dispersion kicks in. So that's not the case. So you can see this in this figure here. And there's a corresponding result which sort of makes this mathematically precise. But what happens is that, once you start with your propagation, so this is in zero magnetic field, okay, you would say that, okay, my edge state is reasonably preserved. If I start here, move ones around, well, it looks kind of similar to this one. We've looked at this figure before. Now I switch on a constant magnetic field. So the next one is 1 over square root of 2. That's the magnetic field strength. So it's perpendicular to the plane. Okay, then you would say, okay, now dispersion kicks in and having a magnetic field here, that doesn't really preserve our edge state. But then what happens is actually that, okay, that's true up to here. But then once you look at slightly stronger magnetic fields again, the edge state is actually better preserved. So a magnetic field is not destroying your edge state, but it changes the damping of the amplitude in a very subtle way. So it can, but it's not perturbative in the sense that the dispersion doesn't increase and increase. So that's another phenomenon that we sort of understood here. The last one is maybe the expected one, that of course you can consider Aharonov-Bohm effect. So if you look at a vector potential that is curl-free, so it induces zero magnetic field, well, then what you find is that this, of course, changes the phase. And as we saw in the beginning, there's a particular notion of phase that your initial state must have in order to properly, propagate around your curve. If you try to alter that, so you introduce a phase that is, for example, orthogonal to the right one, then you will just disperse. And so, of course, since this, the Aharonov-Bohm effect, is precisely about the magnetic vector potential having an effect on the phase, edge states are sort of affected by the presence of vector potentials that do not introduce a magnetic field. Okay, and yeah, so this was actually the last, I think, the last slide that dealt with these phenomena where we see maybe one slide about the proof idea. So it's about this construction of this wave packet. In principle, you can do this to arbitrary order. So what you have to do is sort of like an WKB approaches that you might have seen. You have to solve sort of an infinite hierarchy of recurrence equations. So that's our base operator that we get from sort of Taylor expanding our operator, and then we get operators up to arbitrary order. So these are the operators T1 and Tj here up to arbitrary order. And then roughly speaking, on a very high level, the idea is that, and I hope that this maybe sounds familiar to you and you feel that you sort of know what we've roughly been doing here. You solve that sort of infinite hierarchy of recurrence equation. So initially you solve this T0A0 is equal to 0. Then you solve T0A1 is plus T1A0 is equal to 0, and so on. And then from this, you get these edge states in the end. Okay, and I think, yeah, my time is over, and I'll finish now. And thank you very much for really staying until this late hour here. Thank you.
Thank you very much. Late, but maybe there is one question here. Okay, so first Marius, please. Marius?
Hi, Simon. I wanted to know, so you had a bunch of theorems about propagation. Are there also theorems about dispersion? So say if I take no magnetic field, even straight edge, but I take the wrong starting vector, the orthogonal one, can you then show that there is dispersion?
Yeah, that's right. I mean, it's difficult to sort of quantify this. So I think what you can show is that then you have the usual dispersion you would expect for a Schrödinger equation, right? This usual L1 at infinity bound. So that's something you can show, that these states will just, propagate in a different. They will not propagate along the edge, and then you will just have dispersion. That's right. Yeah. So there are theorems like that where you would say that the usual dispersion bound, I don't know, is sort of attained. So the worst case scenario, if you want.
Okay, thanks.
Please, Massimo.
Okay, so you didn't. Without Massimo. So you didn't talk about the relation of your edge states and the topology of your bulk systems. I mean, you always see edge states, or I mean.
No, there's something like that. So what happens is that what you can show here, I think, is that so you have this couple, right? Which in my case is something like okay, let's go to the straight case, which is probably the one that is most illustrative. So you have your direction of your edge, okay? Let's say that's my direction. And then what happens is that this kappa, it goes to negative values on this side, it goes to positive values on this side. So that's something we sort of assume. And so the sign change of kappa here, that's something you can show explicitly in this case is related to the current, okay? So somehow there's something like the topology is sort of hidden here. in the sense that it's hidden in this kappa, making a sign change on the edge. So if you would take something like, well, I was making sort of that gesture at some point. So if you were taking that kappa is positive here and kappa is positive there, you wouldn't see any of these phenomena. So it's, and okay, I mean, mathematically you see it immediately because this Taylor expansion would not be possible if you had something like that. So there would immediately be changes in the mathematics here. But this effect of having this current, it sort of crucially relies on, you know, kappa having a negative sign here and a positive sign there. And so there are apparently some index theoretic results which also treat our case. We have not really, so I think in simple cases, you can just show it by explicit computations. And so there are results which I think cover this case as well, that they say, okay, you need that in order to get a current, and then you have an explicit expression for the current, but we have not really, sort of, that was sort of not our main interest, but it's true. I mean, this topology is sort of very important here for the result. That's right. Thank you.
Okay, other questions? Okay, please, Johannes.
Did I understand correctly that you said the curvature is the enemy of the edge states?
Well, in some sense, yes. I mean, some certain derivatives that you... Okay, I can show you.
I didn't finish my question.
Oh, sorry.
But nevertheless, the conductivity will be independent of the curvature, right?
Well, okay, that's a good question. I mean, when you talk about the profile, you see at least that it's, if that is your edge state, if you sort of agree that this initial condition is the dynamical state that propagates, you see that what is sort of the maximum. So that's why I include this circle, because to me it's sort of the worst case scenario in some sense, because it has curvature everywhere, right? And then you see this wave packet that starts here, it propagates once around, and then this state has actually decreased. So numerically, you can do that. You can do that. You know, solve that PDE, and you see, okay, my profile has decreased somehow. So at least in that sense, the profile of the edge state somehow changes when you have curvature. Okay, so that's sort of the next to leading order to our sort of result here. So the error bound will depend on derivatives of your kappa. In the straight case, you can see that, so the straight case or the opposite case where you don't have any curvature, you can see your edge state, it stays the way it is. And okay, once you have a kappa that has non-zero high derivatives, the edge state will actually change its profile. Of course, that can mean that you have some, depending on how you define what, you know, your current is, that, you know, it's still okay for you. You will still have your bulk edge correspondence, but just the wave that propagates, that one will actually change under this condition.
Okay. I mean, the curvature, the current must be this. The conductivity must remain the same, if I understand that your sign change determines the topological invariant.
Yeah, that's true, but it. I guess the question is sort of. So I think the question is sort of. Well, when you just look at this wave that propagates. Well, so with the sign change, maybe I should say that the sign change, of course, it depends on us being able to construct explicitly these edge states. Okay, so if the sign change is not there, this construction doesn't work. But on the other hand, so when you now try to explicitly define the current in the let's say the circle case, I'm not sure which result actually treats that case rigorously. Maybe that's something I should say immediately, because of course, because what do we do when we work on this? We sort of linearize our edge. That's, you know, this Taylor expansion. And the case that I'm talking about is the straight interface. There the current stays the same because the wave packet stays the same. And I think that's also the case where I know these sort of rigorous results from index theory, where I know them. There may be others. But I don't know if there exists a result for the circle, okay, for our operator, which says that in that case, the current stays exactly the same. I'm not sure. That's maybe something I just don't know what is known from that perspective there. And in our case, when I said sort of the current, it's preserved. It's sort of infinitesimally preserved because we sort of linearize our edge at every point. So I'm just not aware of any index theoretic result that treats that case, but they may exist. I think I had a discussion with Hermann Schulz-Baldes or some other collaborators of me, and he said that there should be results that prove that in that case the current is the same. But our wave packet is definitely not the same. So I'm not sure what is known from that area for general curved interfaces. But here we see that, you know, things change dramatically, and also in the case when you have a magnetic field, things start to change. So I don't think in this great generality there's such a bulk edge correspondence. Maybe no, but I don't know.
I'm sorry for interrupting. Or you want this? Fine. We have to leave the lecture hall before 9, and this is a threshold we shouldn't violate. So we thank our speaker again, and thank you to all of you for staying for the whole session, and have a nice evening.